So then our next speaker is Natália Móller from the Slovak Academy of Sciences, and she'll be telling us about indefinite temporal order on a superposition of spherical shells. So please take it away, Natália.
Thanks so much for the introduction and also for the organization of this nice conference. And thank you those who woke up early for the morning session after the hiking and the beers of yesterday. So I will talk about indefinite temporal order on a superposition on a quantum space-time that's generated by a superposition of spherical shells. This talk is based on a recent archive that was made in collaboration to Professor Nelson Iacomiso and the Masters of Science Bruna Sago. Let me start doing some brief comments about expressions I'm using in this talk. So you saw in the title the words indefinite temporal order, but a more commonly known expression is indefinite causal order that turned out to be the name of the field, indefinite causal order. And the reason I'm using the first expression is to highlight the role of time and clocks in what I'm going to talk in this work. As it was already mentioned in other talks in this conference, there is a lot of discussion on the meaning of these expressions here, mainly the word causal or temporal in this field. I will not enter on that, just making this brief comment. And those who are a bit more pragmatic that want to refer, sometimes you can find expressions that are indefinite order of operations. Or if you want to avoid any complication or you just don't know what you're talking about, just tell indefinite order and it's all. This set of expressions, they also denote some kind of operation, some kind of protocols that could at least theoretically be performed. And another very common expression that you might have already seen is the quantum switch. And this is one specific test of this kind here, okay? And in this talk, or also the gravitational quantum switch, when we are talking about a quantum space-time, normally we put this gravitational before the quantum switch. And this is what we are going to talk in today. The idea of indefinite order probably had already been discussed many times in the history of science. But one important starting point for the current research was in this work from Lucien Hardy, where he was discussing the radical and conservative features of quantum theory and general relativity. So he was pointing out that general relativity is deterministic, meaning that you have your boundary conditions, you solve your equation, or your Heisenberg equation, you have a unique solution, but it has a non-fixed causal order. I have to first solve the equation, and then I will know if my events have space-like separation or time-like, who is the future and who is in the past. While in quantum theory, we already assume this structure in advance. Normally, we are thinking about some flat space-time, and I already tell I will do this operation before, this after, etc. If I'm thinking about a circuit, for example, but it's irreducibly probabilistic. I just can have probabilities of what's going to happen. And it's expected that if I'm trying to formulate a theory of quantum gravity, that this theory would have these two radical features. And, well, the idea here is to not go directly to this theory of quantum gravity, but formulate quantum theory with no predefined causal order, that is, without this conservative feature, and then it's expected to lead more directly to a lead theory of quantum gravity. It would be easier to generalize that. From this idea, well, Lucien Hardy perceived a work on formalism. Here I will highlight the formalism of process matrix. This is a figure from work of Onion Oreshkov, Fabio Costa, and Czesław Bruckner, who established this process matrix framework. And the idea is the following. So, I don't have a theory of quantum gravity. It's exotic, I cannot think. So let's start about something that I know. I know quantum theory. So let's assume that quantum theory holds inside these laboratories here. Let's say they are closed laboratories. They don't have some access to this more exotic part that could be around them, but inside I will assume quantum theory holds as we know it. So we start from some point that we know how to behave, and then we try to go a little step towards something more general, considering something more exotic here. And in this formulation, events are considered to happen when, well, it's allowed. I did somehow to communicate between them to see what happens. So some target qubit, let's say, is allowed, some target system is allowed to enter in these laboratories, but just once. And what's an event is when I perform some operation on the system. So Alice will perform one operation here, Bob will perform one operation here, but just once. This target just enter once and leave once, and this is what we understand as an event here. And the way that I normally like to think about this closed laboratories in a slightly more concrete example is using this figure here. This is a figure from Bruna, where I would have Alice in her laboratory, perhaps in the beginning of classical space-time, and she crossed at one moment. She's falling on geodesics, so she threw, and then she passed through this superposition of masses here. Then she turns out to be the localizer. But if she's a closed laboratory, she's just measuring the inside, just inner observables. Because of Einstein equivalence principle, supposing it holds in this region, she would not be able to know what's happening in her in this exotic environment outside her. She cannot say if she's in this part of the wave packet or here, or even if there is really this quantum space-time, let's say. So turning back to the process matrix framework, what they did was characterize a large set of, one of the big things, of course, in this paper was to characterize a large set of tasks that would not have a causal order as we know it, like they are more general, what is called as an indefinite causal order. But it's a mathematical results, and how are really, so they have well-defined mathematical expressions, etc. But how are the application of that to a really physical example? There are many operations, and as I told, one specific is the quantum switch. That is the following. I have here this red part denotes this space-time that I don't know what is it. Here I have my closed laboratories. And let's suppose I have a target qubit and a control qubit. And this control defines the path of this target qubit in this place here. So if I have 0, the target go first to Alice, then to Bobby. If it's 1, vice versa. And if I have this control on a superposition state, I would have a superposition of paths. And, well, I can detect here all these in the very end. And I would have this expression here. AB applied on psi, tensorial this control on 0, plus BA applied on psi, tensorial 1 over square root of 2. And, well, this protocol was initially proposed even before the process matrix framework by Cribella and collaborators. And there are many applications on that nowadays. There are experiments and optical tables. But what I'm going to talk here is when we are involving really gravity on that. And the first proposal involving gravity is a paper from Natália Salomé Móller, who is here in the conference, and collaborators. And what they were proposing was that now, let's think that in a closed laboratories, they are equipped with clocks. So here we have the draw of just the clocks, but we should think that I have my agents and they have a clock, and they will perform, or look to the clock, oh, it's 3 o'clock, so I will perform an operation. Okay. So events here are going to be defined through the proper time of each laboratory. And the idea is, let's suppose that I have some massive bag. Of course, this is a cartoon, this Earth here. We should think more about a mesoscopic bag, maybe. And it is, I have my clocks with this fixed distance between them. And for one state of the mass, it is on the right of these clocks, left, closer to B and closer to A here. Because this gravitational field affects the time dilation of the clocks, the time of Bob is going to run slower than of Alice. And the third tick of Bob is going to be on the future of Alice for this case, but on the past of Alice in the other case. So I would have a superposition of past and future, let's say. And in this case, Alice can have a system, apply an operation, send to Bob that after applying an operation, and the other way around here, and then we would talk about quantum switch with that. Well, in this reference, they also debate about Bell inequalities for really detecting a gravitational space-time. I'm not going to enter on that. Just one note before the next slide is that normally I denote Alice and Bob by these clocks here, where Bob is denoted by this black block, just for connecting with the next figures. So, okay, here we have the clocks on this near this delocalized mass, and we are thinking about indefinite causal order with that. Let's now think that I mirror this figure. So instead of having a delocalized mass, I could have a localized mass with delocalized clocks, which I assembled on different heights. And, well, I would have Bob up and Alice down, or Alice up and Bob down. That is, this case corresponds to this, and this one to this one. And just a small comment. Last year, I also gave a talk about this work here in the same conference. We talked about here we developed strategies that would be able to perform a quantum switch using really the gravity of Earth with current technology. Okay? But today, I'm going to talk about more conceptual things. So let's look to these two figures here, and let's think about three questions that come from that. The first one, we have that a quantum space-time, given some symmetries, it can be expressed as a classical space-time. So, what is basically in this image here? So, this is some question that was explored here in this paper of Josh Fu, Rob Nunn, and Michael again. And one question that comes from that is that if I really testify quantum space-time here, etc., what would it, I mean, if this is Earth, of course, I know Earth is classical, but if it's a mesoscopic body, I don't know who is in superposition, if it's the clock or the Earth. What would be the meaning of my probabilities? So, trying to avoid that, one question is it possible to construct a non-geometric space-time to perform a gravitational quantum switch such that I do not need to deal with the symmetries? First question, hold it. Second point, events are defined according to the proper time inside the laboratories, as we have mentioned. But what about other linear observables that could be also important? Okay, proper time is an important property, but there are others that are important. For example, what about the weight? So if I have Alice here in this case, if it measures her weight, she will be able to distinguish if she is in this space-time or this, and the protocol would run for here. So the second question is there a protocol that avoids such possibilities, either this fundamental question and this practical question? It's called it. And the third one is that, let's think about this specific case here, and I want to do the experiment. So I'm an experimentalist, I want to have here my experiment, and I want to walk around. But where I will be located here, because I am in the very end, I'm in classical. So I will fatally measure the weight if I want or not. And I would lead to the coherence here. So for avoiding that, I have to be located in the infinite. Is it possible to have a protocol where I bring the external observer closer and I can think I am really an experimentalist here doing experiments? So think about that questions, these three questions. We started to build on an example that would be of this type, where I would have a classical space-time here, thinking that I can walk, and inside this bounded quantum space-time. Would this exist? What we mean about classical space-time? So, very simple, exactly like Einstein did for general relativity. I have a net of clocks, ideally one clock for each point of this space-time, and they can measure classical observables, and they can communicate, not through this classical space-time, and they will always agree. This is the classical space-time as what I am mentioning as this notion. And about the quantum space-time, of course, it's much more difficult to decide what to do, so we have to rely on some hypotheses. And what we decided, we chose to assume for being able to find some concrete solution is the following. We suppose that the gravitational field can exist in a superposition of semi-classical states. So I suppose I have two configurations of mass, the localizing mass, that could be on the right or the left, for example, and one generates one space-time diminu 1 and the other diminu 2. I can just make a superposition of that, and this would be the generated space-time. The second assumption is that events are defined operationally to proper time, and that for each event in one of the branches of the space-time, I have one correspondent in the other one. So they are always in pairs. And the third assumption is that the dynamics can be computed semi-classically in the same way of the assumption 1. So I have the geodesics or some motion in one space-time, I have a motion in the other, and I have the superposition of that. Okay? This is not like assumptions for talking about the general theory, it's assumptions for this specific example. Okay? And what now that we have the setting established, we can talk about the specific quantum space-time we are going to do with. What we are going to consider are the superposition of two space-times that are spherical shells. So, for the first case, I have a distribution of mass on the surface, so this ball is empty. Inside I have a flat space-time, and outside I have a Schwarzschild space-time. On the other case, I have two spherical shells, so inside here is also empty. Also here, this part is empty. I have a distribution of mass here and here. So here I have this Schwarzschild, here I have flat as well. Here I have the Schwarzschild 2 because of this distribution of mass, and here you have another Schwarzschild that happens because the sum of both here. And we chose such that this will be the same Schwarzschild as this. So outside both boundaries, we have this classical space-time. Okay, so here I have the situation that we are considering, and I want my laboratories, my agents, Alice and Bob, to go through this quantum space-time. So I need to consider when it's also crossing the border. So Schwarzschild and flat space-time, we know from textbooks, but how do I go through this border? Well, this is also textbooks, but it's a bit less common to know. What we considered was these conditions in these textbooks here. And I will just take the first Schwarzschild for simplicity, the first spherical shell for simplicity to explain how we compute the dynamics on that. I wanted to know how is the rate of proper time just before and just after this boundary, okay? So how it is just before and just before after the coordinate time for some external observer and also the proper time. For doing that, we already have the metric of the outside of the Schwarzschild. So we consider this metric on this 3 + 1 dimension, and we induce a surface metric on the surface that is 2 + 1. So the 2 dimensions of space and time for this metric here. Okay, and the same for the inside. So I have one metric for the surface here and one metric for the surface here. What I have to impose is that they are the same, because I am like with the same surface, but looking from the inside and from outside. And with these junction conditions, we can compute the rate, the difference of rate with that. And in general, they are not continuous. Okay, And now, so we have a way to compute the whole trajectory of a laboratory crossing this shell. And for both spacetimes, it is like the same. I just have to iterate the same procedure here. And let's talk about how do we do the quantum switch with that. So what we are going to consider here are Bob, the target, and Alice. Just Alice is going to go through this quantum spacetime. The target and Bob keep outside on the classical part. So in the first moment, I have Alice on the shell. It is going to fall. So in the first moment, it just falls one trajectory, one single trajectory, because it's on the classical part. And when it crosses the border, it will be divided into two. Oh, my animation, it was so beautiful. It's not going well. Yeah, okay. And because there is a delay. But you can see one of the wave packets arrived before on the target than the other, and we do in a such way that the proper time of one wave packet when it arrives on the target and the other wave packet when it will arrive on the target after is the same. Because instead I could distinguish that I'm arriving different times. After that, Bob will apply the operation, and then the second after that, Alice is going to apply again. After that, well, here my artistic abilities are over, so I will show you the graph of the full trajectory. Alice is going, one of the wave packets are going to oscillate with one frequency somehow, and the other wave packet with another frequency. But we built this example in a way that in the very end, they meet again. So they are both like going up and down, but in the very end they meet in the same coordinate time, in the same proper time as well. So the inner structure of these laboratories is absolutely the same in the very end. Okay, here in this picture we have this specific moment here, okay? But this would be the full trajectory. And how do we find the solution? So first thing is that we set two free parameters that we chose to be the two outer radii. And we set two conditions. One is that the proper time of one wave packet on one oscillation, so like in one oscillation like this, divided by the coordinate time of the external experimentalist, is the same of for the other wave packet. And this guaranteed that when they meet again, the proper time is the same. But could be that they would be keep oscillating forever and they would not meet never again. For guaranteeing that they will indeed meet again, we can impose that this difference here, this ratio between the two coordinate times, is a rational number. So P in this case would be 3, 1, 2, 3, 4, and the other 3. Okay, so I would have here P over 3. But how to find that? We plot in this graphic here, we plot these two solutions. So here I have in blue one and in orange the other one. And when they meet is the moment that they are equal. So here I have a continuous of solutions. Okay, all this graphic is analytical, it's calculations. Just the moment of find, but I wanted to find now a solution here in this continuous that has the number, the rational number I have. Since it's continuous, I will have a rational number. I just have the work of choosing a good one that's not like 1,000 over 327, but 3 over 4 is better. And then we can, but you can also backwards compute that check this analytically. Okay. Okay, great. Yes, we did quantum switch, but and what? Why did we do all that? How long time? How many? 2 minutes? So I will jump a bit some calculations that I have for this ending, but let's compare this different approach here. What is the difference between these two examples that I told and the one with the geodesics and the spherical shells? Let's suppose that I will perform the quantum switch and I will allow interventions of the agents. So instead of Alice just applying operation A, she will measure some ancilla she has on her lap, could be even some quantum state, and she will perform an operation that is a function of this internal observer. So she will do an operation that if I obtain different results of the measurement of my ancilla, I have a different operation. Okay, she will perform then C or D if they are different. Yeah. So suppose that for some quantity little a, I have the operation A that was talking all the time. Then the protocol, when this for the two branes I have this A, the quantum this equation that resembles a quantum switch of this A, B, and this B and this curved A would be indeed the quantum switch as we use it to express. But if these two things are different, then I would have CB plus BD instead of AB plus BA. That's some quantum switch. So if the same for both, similarly, okay? And for this case, if I decide to have lambda and eta, it is this quantity for both, to be the weight, for example, could happen that I don't perform the quantum switch, I perform just an operation, CD plus EF. And this means that Alice and Bob must be systems that are insensitive to weight. While in this case here, they could be any inner observable. I could measure height, weight, or anything that is inside, because I would have always that I have a BA plus AB plus BA. And this means that because by construction, we always have that the inner observables, they are the same in this sequence. And this means that here, Alice and Bob must be things that are insensitive to weight. Here not, meaning that the quantum switch depends only on the external environment and not on the laboratories. Well, I think my time is over. So, for just a short summary, we have that superposition. We have constructed superposition of non-isometric spacetimes. The external observables are well defined on a classical region. And we computed solutions for the Alice's trajectories. Alice followed geodesic paths, and because of that, it can apply any operation that are, or even those that depend on the weight. And this is the most accurate example of a closed laboratory. Thank you very much for your attention.
Questions, Natália? Sure. We do make a learn and then Joe.
Yeah, I don't want to jump first, but yeah, thanks. That's a very elegant work. I'm curious if you had a look also at the numbers like in your previous works, even just for the fun of it, like what would be the weight of the shells you could consider?
No.
And,
yeah, no. I think it's quite theoretical, and we thought about comparing it, but it would be so unrealistic to a real realization that we didn't really. But thanks for your question.
I'll ask my question in coffee break, actually. It's a bit complicated.
Okay.
Do we have any one last quick question for Natália? If not, then maybe we can just move all the other questions to the coffee break. Thanks very much.